this video, we'll be looking at the third section of the particle physics booklet, focusing on photons. Now, before we can understand photons and this new concept, we have to consider electromagnetic radiation as a whole. At GCSE, you'll have been introduced to the 7 different types of electromagnetic radiation, with the one commonality that they travel through a vacuum at the speed of light and are transverse waves. The reality is they are the same thing. They are just light at different wavelengths. So when we give these different named labels to different parts of the spectrum, it is all just part of a whole. The whole reason that they're given individual names is based on their behavior when they interact with different things and are observed and used for different purposes. But in general, they are the same. They are waves of light. And their general wave behavior will be consistent. Now, knowing details about each of the 7 types is not critical at this level, but it is worth making sure we have a solid basis to work from. The wavelength and frequency values can actually prove useful in supporting answers, giving you a gauge of whether or not you're in the right range, for example. So starting with our highest frequency and lowest wavelength, we know that gamma rays are going to have a wavelength less than 10 to the minus 12 meters, and their frequency generally in the high end 10 to the 20, 10 to the 24 hertz. Now, in terms of uses, we know that gamma rays are used quite commonly for sterilization, that they're used to clean medical equipment, for example, killing off bacteria, and they're used in cancer treatment, where high-intensity gamma rays focused on a target can kill cells, including cancer cells. Hazard-wise, it's commonly known that, again, intense gamma rays can cause cancer. So causing cancer is a risk of being exposed to them, simply because they can damage your cells, damage the DNA, which will inevitably cause cancerous effects. X-rays are the next one along, these having a slightly bigger wavelength. So we're talking 1 nanometer to 1 picometer. So 1 times 10 to the minus 9, 1 times 10 to the minus 12. And the frequency range will again carrying on 10 to the 17 to about 10 to the 20. So we're going to see this flow moving down the low end to high end, and so forth. Now, in terms of uses, X-rays are obviously known for medical imaging. X-ray machines are the most commonly known, but things like CT scans are a 3D variant of this, using multiple X-rays to map a 3D image. We can also use that same principle when looking at matter, so looking at solids to find the structure of the atoms using crystallography. So X-ray crystallography is quite an important thing to understanding structure. Hazard-wise, it's exactly the same as gamma. We still have a large amount of energy being transmitted, therefore causing cancer is the big risk. And the overlap between these two in terms of their damaging effects is quite high. They're very, very similar. Next down the line, we have UV, ultraviolet, ultra, meaning above, so it's at that end of the visible light spectrum. Again, we're going to go from 1 nanometers all the way down to 400 nanometers. And our frequency range 10 to the 15 to the 10 to the 17. So we're getting smaller brackets now with this. So it's a much more exclusive sector in terms of its uses. Now UV is known to cause a glowing effect. In America it would be called a blacklight. And it can cause certain chemicals to glow. But we also use it for things like cleaning. It is still a high energy wave, so it can still be used to clean off surfaces and kill off bacteria, usually with a high intensity UV, but nonetheless it will work over time. But as we said, fluorescence is a huge factor, and fluorescent lamps, for example, will also use the effect of interacting with chemicals. Hazard-wise, this is the lowest energy wave that tends to have the ability to cause cancer. So causing cancer is still a major effect, but generally UV will not be able to penetrate very deep into the body. So it's more likely to cause skin cancer than any other type. Now in the middle of this spectrum, we have visible light, which has the smallest range. And the only reason we classify it is because it's the only one we're actually sensitive to, the one we observe. So this ranges from 750 nanometers to 400 nanometers, give or take. So the 400 end will be the violet end, the 750 will be the red. And in terms of frequency, we have value of around 4 to 7 times 10 to the 14 here. Now in terms of uses, visible light seems too obvious to say seeing, so we can think of one thing that emits it, such as a torch, and something that absorbs it and utilizes it and controls it with things like lenses, so a camera or a telescope, something like that. Blindness is a potential risk. That's down entirely to intensity rather than being due to any damaging energetics. It's just overwhelming the cells and causing them to shut down. Now infrared, this is where we go below red on the spectrum. Again, getting bigger, so we got 2.5 micrometers this time, all the way down to our 750 nanometers where red was. And our frequency will continue to drop as well. So going to a range of 10 to the 13 to 10 to the 14 in terms of hertz. Now uses infrared, again, we can emit it or absorb it. So absorption, the most common example to think of is thermal imaging, where you're interpreting thermal output of other objects. But also you can emit it in heaters and anything that emits heat. Therefore burn is a risk. But again, it's not the same element as the first three in terms of damaging DNA and penetrating the body. This is just brute force intensity. And it's the last one that has any real risk. Microwaves and radio will have nil. So considering microwaves then, they will continue to gain a longer wavelength, and this time reaching actual measurable values with 1 millimeter to the 2.5 micrometers. So we're in a scale that's more understandable to us now. The frequency will obviously continue to drop, And we start stating it as 3 times 10 to the 11 to about 10 to the 13. The only reason 3 is appearing at this stage is relating to 3 times 10 to the 8 for the speed of light. Don't worry about it, it's just to give you a rough gauge. In terms of uses, obviously we can say microwaves are used for cooking, but that is really a resonance effect that will be covered in actual relevant detail in the waves topic, where you understand that process. Otherwise, communication is the primary use for microwaves. Mobile phones will use microwaves because they are able to penetrate the atmosphere, the ionosphere. Now, radio waves are going to be the biggest. So now we're going for anything greater than 1 millimeter as a wavelength, and a frequency less than 3 times 10 to the 11. That was the limit on the previous one. In terms of uses, the only relevant use for radio waves is communication. That includes listening to music on the radio, etc. It is a transmission of a signal carrying data. So that's the entire spectrum. Now moving on to new content, we have the concept of photons being introduced. Now light has gone through a very interesting, complicated history in terms of trying to understand what it is. But there was an experiment that required a new understanding, the photoelectric effect, which we cover later on in this booklet. Now, this new theory of light stated that instead of a continuous wave, energy was being transmitted in bundles, in small discrete packets of energy, meaning they would have a set specific amount of energy in one transmission. So these photons would be replacing the concept of a wave with something more like a particle, but not actually a particle. Now, as we understood, waves anyway are affected by frequency, as illustrated by the electromagnetic spectrum. An equation was formed utilizing Planck's constant to show this relationship. So we have E equals hf. E is our photon energy measured in joules, and h is this new value, the Planck constant, which is simply a constant that scales to the smallest measurable values and takes the form of 6.63 times 10 to the minus 34 joule seconds. And this is provided on the data booklet, and it is a number you will become very familiar with. F, as expected, is simply frequency measured in hertz. And just to make sense of the Planck's constant unit, hertz, remember, is the same as per second. Now, you won't always get the frequency given. You may instead be given the wavelength, which means that you will need to translate the frequency into wavelength or vice versa. This can be done using an equation very familiar from GCSE, with speed is equal to frequency times wavelength. At this level, this is placed in the waves section of the booklet, and the symbol c is used for the speed because we're generally referring to the speed of light, 3 times 10 to the 8 meters per second. And lambda, you should recall, is the symbol for wavelength measured in meters. Now, conveniently, in the data booklet itself, they provide you with the full equation for photon energy, showing both variants, where you are given it as E equals hf equals hc over lambda. So there's never really any rearranging necessity. You simply choose the part that you can use. Now, unfortunately, measuring things like photon energy in joules is not very effective because we always end up with an exceedingly small value, usually in the range of times 10 to the minus 19 or times 10 to the minus 20. So to simplify matters and provide values that are a lot quicker to use and a lot easier to use, we use a new unit, the Electron Vault. Now, this is simply given as 1 electron volt is 1.6 times 10 to the minus 19 joules. Well, this value should be familiar. It is the same as the charge of an electron, E. So that's why it's used here. It's very easy to convert. If we want to go from electron volts into joules, all we have to do is multiply our electron volt value by the charge of an electron. And vice versa, if we wanted to turn joules into electron volts to simplify matters, we simply divide by the charge of the electron, 1.6 times 10 to the minus 19. This will come up more and more as we go on to next year's content as well, but it does just exist to make matters easier for you. So it will make things easier to reference and easier to calculate. Now, to look at an example for this, we are going to consider a photon as given here with a frequency of 5.08 times 10 to the 14. Now, we need to find the energy in units of electron volts. So when it specifies the unit, you need to ensure that it is provided to that unit. Now, luckily, given frequency, we can use the easiest form of this equation, E equals hf. So we take Planck's constant, 6.63 times 10 to the minus 34, and multiply by the frequency that's given, 5.08 times 10 to the 14. Plugging it through the calculator will give you a value in the range of 10 to the minus 19 minus 20. So we end up with a value of 3.37 times 10 to the minus 19, as expected, and that's in joules. So knowing it's in that range, electron volts makes sense. All we need to do is take this value and divide it by the charge of an electron. So we're going to divide 3.37 times 10 to the minus 19 by 1.6 times 10 to the minus 19. Now, seeing both of these have times 10 to the minus 19, they will cancel out, allowing us a simple equation of 3.37 divided by 1.6. So we should expect a simple value at the end of this, which is exactly what we get. So we end up with a value of 2.11 electron volts. Much simpler, much shorter, and much less likely to carry an error while we use it. Thank you for your time.